So it's in the lecture notes, it's 1504, but in the textbook, it's the second half of chapter 17. So that's what we're discussing in today's Zoom session. I want to first make sure that you understand some of the vocabulary that we are going to be discussing. So let me go ahead and do that. Remember when we had a reaction, say a reactant goes to product, and let's say that these are in the gas phase, and we write our ice table. Some people call it RICE because this is the reaction, the initial, the change, and the equilibrium process. And so what we have is some concentration of the reactant. Let's say it's about 0.67 molar, and no product is formed. And then we use X to show the change as the reaction progresses. Well, when we have a chemical that starts to dissolve in solution, let's say we have an ionic substance, it's metal and an anion, and it starts, and this is a solid. Generally, we start with a solid and goes into its ions. And the ions are soluble in water. And let's say that we have an initial, a change, and an equilibrium condition. Well, for a solid, there is no concentration. So it's just a solid. So we can just put solid here. Because remember, a solid is not involved in the mass action expression. So we don't write down the concentration. But before it dissolves, this is 0 and this is 0. That's the amount of ions of this particular chemical before it starts to dissolve in solution. But now instead of X, here we have minus X, and here we might have, let's say this is 2, this is plus 2X. We don't indicate in this type of problem an X value. We actually call it an S value. So we said that some of this will dissolve, but when they dissolve, then they form ions. And so our S here is like our X here to indicate the progression of a reaction. But the S is called the solubility, because that's how much of the chemical goes into solution. So when I say the reaction, well, the chemical starts to dissolve and I do an ice table, instead of using X, I'll use S in general. You could still use X, but know that when a substance is going into solution, it's called the solubility, okay? And because solubility starts with an S, we indicate it as an S variable. Solubility has two definitions that you guys will see later on. And one of them is how much of the chemical actually goes into solution. So let's go ahead and get started here, just so that you understand that when something dissolves, the amount that dissolves is the solubility, okay? So let's take a look at this reaction. This is a reaction that involves, in this particular case, barium sulfate. So barium sulfate is an ionic substance, and you know it's ionic because it's got a metal and an anion, okay? It's got a cation and anion. That's how you know it's ionic. And when this thing dissolves, it breaks up into the ions that forms it. So you have to make sure you understand the identity of your ions. Like for example, if I have, say I have barium, actually that's barium. Barium is a +2, okay? And so in this particular case, barium phosphate, PO4. You guys know that phosphate is a -3 ions and barium is a +2. So you better know the formula that it's Ba3PO42. If you don't know that, then number one, make sure you get yourself a good list of polyatomic ions, and then just know the chemistry of how to write formulas. When this thing breaks apart, then the phosphate doesn't break down to phosphorus and oxygen. Okay, that's because the phosphate is a stable polyatomic ions. So you don't break it down any further. Just like the sulfate here doesn't break down to sulfur plus oxygen. Sulfate is a stable polyatomic ions. Okay, so make sure you understand that. Another example that you will see is this guy right here. This chemical right here is barium biphosphate. This is a stable polyatomic ion. So this thing will break down to barium and biphosphate. Because the phosphate now has a hydrogen, the charge goes from -3 to -2. So please review polyatomic ions and ionic substances if you're a little confused on this, because this is part of the chemistry 200 that you have to bring in order to understand some of the topics that we are discussing here. Okay, make sure. So let me go ahead with this example. Let me clear this real quick. So when this ionic substance dissolve, then the reaction is barium sulfate goes to barium plus sulfate ions. Those are the two ions that it breaks down to. And so the equilibrium expression, the mass action expression, is products of a reactant. But remember, the reactant is a solid, so it's left out. So the expression is reduced down to this right here. K equilibrium is equal to the barium concentration times the sulfate concentration. But we don't call it K equilibrium anymore. We call it the K solubility, the solubility constant. Okay? There's a difference between the solubility constant and the solubility. The solubility constant is a constant like an equilibrium. The solubility is how much of that chemical goes into solution, like X. Don't confuse the two. So that's basically what we have here. The solubility constant gives you an idea of how much ions are in solution. If there's a lot of ions in solution, that KSP will be large. But if there's little ions in solution, that KSP will be small. In general, KSP is small, okay, in general. So let's take a look at this movie so you can visualize what is going on when something is in water. This might be barium sulfate, where barium is the positive and sulfate is the negative, or most likely sodium chloride, NaCl. But the chemistry in which water goes in and stabilizes the ion, whether you have barium sulfate or sodium chloride, is still going to be the same. It's the hydration interaction that stabilizes these ions that causes it to dissolve. So let's take a look at this, okay? And there is no sound. So this is your water molecule. And because water is polar, it will orientate itself so that the partial negative charge of water is attracted to the positive cation, and the negative partial negative charge of oxygen is going to be attracted to the positive cation. Okay, remember, opposites attract. So here we have sodium chloride, and now what's going on is this is how water hydrates and basically tears down the ionic substance, the crystalline lattice of an ionic substance. It goes in there, stabilizes it, and rips it off. And then that's the dissolving process. Okay, that's basically what's going on. And so when you write aqueous, it's basically because of that right there. The aqueous means that these things are separated by by the aqueous means that the water is stabilizing these ions. That's what aqueous means. And now it's dissolved. So let's move on. Solubility. What is the meaning of solubility? I told you there was two definitions. So, number one, solubility is how much of the chemical goes into solutions. It's a quantity, okay? Um, it's defined based on the amount that goes into solution is defined based on the temperature and the identity of the ions. But solubility also tells you that the chemical is going to dissolve in water. Okay, when you say something is soluble, then you say that it can go into water. When you say something is insoluble, you say that it generally forms a precipitate. Let me tell you a little secret though. When you put a substance into water and it's insoluble, some of it actually goes into solution. Okay, there's still a very, very small quantity that goes into solution, but the majority of it doesn't dissolve. And so what you see is a precipitate, which tells you that it's insoluble. So the second part, like right here, is the solubility is expressed in grams per 100 milliliters of water. When you see a value S, then generally it's going to be the mass of that substance in 100 milliliters of water. Okay, or you can express it as grams per liter if you have 0.10 liter of water, that is. Okay, um, sometimes we don't, in the equilibrium, we don't deal with solubility as we deal with molar solubility. Molar solubility is converting the grams to moles and then dividing that by the volume of the solution. Okay, so make sure you know how to do that conversion. You should be able to take a solubility, that is the grams per 100 milliliters of water, and convert it to molar solubility, because molar solubility is the quantity that you guys will be using when you solve these types of problems. So the other thing I want to make sure that you understand is that when something is soluble, it basically means that you see very little precipitate. Most of it is going into solution as ions that is hydrated by water. When you see something that is insoluble, then what happens is you see more precipitate. Basically starts to form some solid. Okay, so solubility means it's going into solution. Insoluble means that it's crashing out of solution. And this is important because that's how a lot of the questions are going to be stated. And you'll see that as we work on some math problems. Factors affecting how much of the chemical will dissolve. And you guys know this, if you take some sodium chloride and you want to get more of it into water, you basically can change the temperature, okay? Or you can change the nature. The first part here is the nature of the solute. Potassium nitrate, as we saw in the chart last time, solubility chart. Well, I think we're going to be seeing it shortly here. The nature of the chemical, some substances are more soluble than others. Okay, so depending on what chemical you have, you're going to have more chemical, some chemical dissolving into water more readily than others. But there's also a temperature factor. The temperature factor is more important. Remember that solubility can also apply for gas. How much of the gas goes into solution? Although we think of solubility in terms of a solid going into a liquid, you can also get a gas into the liquid, and that's also its solubility. When a liquid goes into a liquid, it's called miscibility, by the way. But for solids and liquids, the temperature plays an important factor. What happens is that when you raise the temperature of the solution, the water now has more energy to crash into the solute and break it apart and then stabilize it. On the other hand, when you put a gas into solution, say you dissolve gas in water like carbonated beverage, you guys already learned from last time that the kinetic energy of the water and the kinetic energy of the gas allows the gas molecule to start to escape that interaction. And so you decrease the solubility of a gas when you raise the temperature. And that's what we see right here. Okay, you actually decrease the solubility. It's not going to go into solution. For a solid and liquid, you generally increase the solubility. For a gas, you decrease the solubility. How about pressure factors? Well, if you want to put something into solution, solids are generally already tight together. So increasing the pressure for a solid to go in solution does little or anything. On a gas, however, you're basically squeezing that gas into the solution, so you increase the solubility. So it's just the opposite. For solid and liquid, very little effect on the solubility. For a gas, it definitely increases the solubility. So for a reaction to take place, we generally want to make sure that these chemicals are interacting and colliding. And so the best way to get a reaction to go is to dissolve it in some aqueous solvent. The reactant, hopefully one of them, hopefully your reactant, if it's a solid, is soluble in water. That way they increase the number of particles that can collide, and therefore you can get some reactions to occur. So I think there was a question in the last exam about how can you, what's the best way to increase the rate of the reaction. And it's basically one of the best ways is to make sure that there's a lot of particles involved. And the best type of chemical that does that is when an ionic substance can dissolve in water. Okay, so again, when a reaction proceeds, the reactant needs to go into solution so it can collide with each other, and then the product forms. And generally what you want is you want a product that is not soluble in water. You want a product that is insoluble in water so that it separates. And when it separates, then you can collect that product via filtration. And this is important because what you guys will see is that when you do the evaluative report, experiment 6, that's exactly what's going on. You saw it as well in experiment 2. You'll see it in part in experiment 3, in which you have a chemical and you put it in solution and it's dissolved. And then you have another chemical, you put it in solution and it dissolves. But when you mix it, a precipitate forms. And that precipitate is generally the byproduct of that reaction, but it's not soluble in the aqueous medium. And therefore, using its physical properties in solubility, you can isolate it. So when a precipitate forms upon mixing of two solutions, it is a result of a new species that is present in the solution. It's the new species, the byproduct of the reaction. So let's.
I have a question about that.
Yes.
So it's not a, it's just another one of the products that's made from that reaction, right?
Yes.
Do you not want us using the word product? It's just a new species? Or
no, you can use product. I'm just kind of using the different words so that you understand that it's produced, it's a product. And you got to remember though that sometimes when you mix two reactant and you don't get a precipitate, it's because it doesn't form a insoluble product. And so you actually don't get any reaction. Even though in paper it looks like you have a reaction because it's a double displacement reaction, but because it's still dissolved, it still exists as an ion and you can't isolate it, then really there is no reaction.
Okay, yeah, and that it would just be like a rearrangement of all the ions, but they're still separate.
They're still floating in solution. Exactly.
Okay, thank you so much.
Sure. So let's take a look at this because this is an important in terms of solubility. Let's say you form two reactions, like I just previously said. You've got two solutions, silver nitrate and hydrochloric acid, or maybe not even hydrochloric acid, let's say sodium chloride. And you guys know that the solubility of chlorine salts generally are soluble. Anything with a halogenated anion are soluble, except there's the exception, and I'll show you the solubility rules in a later slide, except if the cation is lead, mercury, or silver, in which case you have a product that is insoluble and a precipitate forms. So that's exactly what you see here. If you have silver nitrate and sodium chloride, then you get silver chloride and sodium nitrate. And even though this is the product as written in the reaction, the fact is the AQ tells you that they are separated, that they are still dissolved in water. The only thing that you guys are going to be collecting is that silver chloride precipitate. And so if you want to know about the equilibrium of this, then we say it has an equilibrium. And you can certainly write the mass action expression. And the mass action expression is going to be based on the net ionic equation. So you got to go back again and make sure you understand how to write a net ionic equation. And the reason why we use a net ionic equation is because it's only those species responsible for the precipitate that is what we pay attention to. So the net ionic equation really is silver plus chloride goes to silver chloride. That's the net ionic equation. The net ionic equation you can always determine because if you know the precipitate, it's only those species, those ions that are in that precipitate, the silver and the chloride in this case, that is going to be involved in the net ionic equation. The other chemicals, the other ions are what we call spectators. Remember that? Anyway, this would be the reaction we have, but we have a nomenclature in chemistry that whenever we have a precipitate and we know the net ionic equation, we don't write it as a precipitation reaction. This would be a precipitation reaction. Okay, let me make sure you understand. If we have a reaction, we get a precipitate, then yeah, that's a precipitation reaction. Generally, it's like a double displacement reaction. But we don't write it that way when we're trying to figure out the equilibrium. We actually write it as a dissolution. A dissolution is when you have the solid going into its ion. So instead of writing this reaction, we would write this reaction. And you can see that this is just the reverse of that top one. And so this KSP, this K equilibrium, which we now call KSP because it's a solid going into solution, is equal to this equilibrium here, but because it's the reverse, it's the reciprocal. Okay? So the KSP is the reciprocal of the precipitation equilibrium constant. So I just want to make sure that's clear because that's the nomenclature that we use when we're dealing with ionic substance. And so let me just clear this so that you can see the rest of these slides. This right here is just the movie of what goes on when you have this. And for some of you who are in lab, then you will be doing some of these reactions. In fact, you will be doing one of these reactions indirectly. It's the cobalt chloride, cobalt hexaqua reaction, and you add a little bit of silver, and the silver actually removes the chloride from that main equilibrium and forms this precipitate. So even though the silver is not part of the equilibrium for the cobalt compound, it affects one of the chemicals. And so that's the reaction that you see here. And so let's sorry about that here. So the net ionic equation is that, okay? You get a K equilibrium from that reaction, but we write it in the reverse. That's the standard convention. And so for the precipitation reaction, and we write it in the reverse, we have that. So our KSP, which would be, again, the dissolution, is the reciprocal of the equilibrium constant for the precipitation reaction. Remember that whenever we reverse a reaction, we don't give that quantity a negative value. That's only for thermodynamics. When it comes to equilibrium, it's the reciprocal. You can never get a negative equilibrium constant. Again, let me stress to you that you guys need to know the identity of your polyatomic ions. Here's a problem where I have sodium. Um, it's basically ethoxide. This oxygen, CH2, CH3 is an ethoxide, and that particular chemical breaks down to sodium, hydroxide, and ethanol. So the KSP for that, because notice it's a solid on the left, is equal to sodium times hydroxide times the ethanol. This is ethanol concentration. So in general, for most of the chemical that we are dealing with, there's only a cation and anion, but there are some problems where you might get three species in the reaction, different ions, different species, and you need to know the identity of these chemicals or know the chemistry in order to figure out what the products are. You need to know what the reaction happens to be. Okay, but in general, for an ionic substance, they always break down to their cation and their anion, and generally the anions are the more difficult ones to figure out, and so get yourself a good list. So let's take a look at this silver phosphate. Silver phosphate is generally insoluble in water, and so what we have here is silver phosphate goes to silver plus phosphate. Know that phosphate is -3, therefore you need 3 silvers to make that electrically neutral. Okay, so this right here is the molar solubility. Not just the solubility, but the molar solubility, indicating it's the moles per liter. If I ask you to calculate the solubility, S grams per 100 mils of water, you should be able to do that based on what you guys learned back in chapter 13. But here, this is the molar solubility. And so if you want to solve this, what is the solubility product? That's the equilibrium constant. Then you can certainly write the ice table. And when you start out these types of problems, always write the ice table first. That way you can take into account the ions, because some of you will just do this. Oh, the KSP is just equal to, that's the solubility, it's equal to the silver cube times the phosphate. And since the solubility is that, then that's what you're going to do. But to solve this type of problem, it's best to do it from the ice table. And let me show you why. Let me clear this first. Okay. The reason why you need to do that is because of the following. We have our initial, this is going to be a solid. This is 0. Change my color. And this is 0. Nothing has dissolved yet. And then the change is minus S plus 3S plus S. For every one of the silver phosphate that dissolves, for every 1 molar that dissolved, you form 3 molars of silver and 1 molar of phosphate. That's why it's a 3S to an S ratio. Then at equilibrium, this is just a solid. Doesn't matter what that is. It's a solid. It doesn't show up in the mass action expression. So you don't have to worry about it. This is 3S and this is S. So the KSP is equal to 3S cubed times S. Now 3 cubed is not 9. That's a common mistake. 3 times 3 is 9, but 3 cubed is 3 times 3 times 3. That's 27. Okay, so make sure I'm trying to alert you of common mistakes I've seen in the past. 3 cubed is not 9. 3 cubed is 27. So this is actually 27 s to the fourth. Okay, this is 27 right here, and then there's an s cube, and then you multiply it by s, so it's 27 s to the fourth. And so in order to calculate the KSP, and we know the solubility, you just take 4.4 times 10 to the minus 5, raise it to the fourth power, and multiply it by 27, and that's the solubility, okay, or the KSP. So remember that this is a very, very small number, 10 to the minus 5. And so when we do this, let me just show you that real quick in terms of the math. Here I substitute S for that, 3 times that. And so when I do this, it's going to be, that quantity is 1.01 times 10 to the minus 16. If you do that math, 27 times 4.4 times 10 to the minus 5 to the fourth, that's equal to 1.01 times 10 to the minus 16. It's a big negative number. In other words, the amount of silver phosphate that actually dissolves is very, very small. That's why we say it's insoluble, because only the amount of silver or the amount of phosphate that you find in solution is going to be 4.4 times 10 to the minus 5. And that's true whether you put 1 gram of silver in that solution or half a gram, because 1 gram and half a gram are going to be a solid. And so you're going to get that amount. Okay. So that's how you would solve these types of problems. You can see that the problems are somewhat easier and somewhat more complex. It's easier because you don't have to deal with a reactant. The reactant is a solid. But it's more complex because now, depending on the number of ions you have, you got to raise it to that power. That's the complexity of it. Okay. That's why you need to know what the ion identities are, because if you don't know the ion identities, then you don't know how many ions are going to form. That's the key. So,
All right, I have another quick question.
sure.
Could you go over just briefly again? I'm having trouble understanding what S means, like conceptually. I understand like the math and everything, but what does it mean conceptually?
Okay, let's say I have a beaker. Okay, and let's say I've got some silver chloride in here. You know that silver chloride's insoluble, right? Just based on the solubility rule.
Right.
But I already told you that even though it's insoluble, you still get a little bit of silver and a little bit of chloride. Not a lot, okay? Like 10 to the minus 6 or 10 to the minus 7. That right there is S. That's how much goes into solution. Is that sort
Okay.
of clear? So the S value is, because for every one of these forms, so that's really S. For the amount of the molar amount of the solid that goes into solution is S. Of
Okay.
course, if we have silver phosphate, okay, and you get 3 silver and 1 phosphate, the amount that goes into solution is still S. But now this is 3S and this is S. Does that make sense?
Okay. Yeah, got it.
Okay.
Got it. Thank you.
No problem. Sometimes that's why I like to draw things, because you can easily grasp it rather than the words that I say. Okay. So that's why I also stress that if you guys are confused about a reaction, kind of draw yourself a diagram. That way you can visualize what's going on, and it always makes it a little bit more clear. So good question.
Yes. Okay. Thank you so much.
No problem. So let's take a look at this, and remember this especially for experiment number 6. Okay. Sorry, experiment number 5, because this is one of the things that you guys will be using in that experiment. In fact, this calculation that we will be doing is probably a calculation you will be doing for experiment number 5. This is called a solubility chart. And we talked about the solubility chart. I don't know if it was last time. I think it was last time. We talked about it last time in terms of Le Chatelier's principle. But here, I want to show you the quantitative calculation in terms of KSP and solubility. So you can see right away that potassium nitrate is going to be the most sensitive chemical in terms of solubility. Very little change in temperature causes that chemical to dissolve readily. Versus sodium chloride, okay? Not much of it dissolves even though you raise the temperature, but it still starts to dissolve. More of it goes into solution. More of it dissolves as you raise the temperature. Of course, cerium sulfate is a chemical that does the opposite. The solubility decreases. You get more precipitate forming. So let's take a look at this right here, because this is maybe a question that might be thrown in there. The solubility of potassium nitrate at 20 degrees is 30 grams per 100 milliliters. And how do I know that? This right here is potassium nitrate. So you go to 20 degrees and you look at where the 20 intersects the potassium nitrate tie line. This is called a tie line because that's the graph. And you see that it's 30 grams in 100 milliliters of water. That's what I said. What is the KSP of potassium nitrate at this temperature? Assume the volumes are additive. In other words, if I have 30 grams of solid and I put it in 100 milliliters of water, then the 30 plus the 100 is 130, okay? Generally, that's not always true. But if you make that assumption, then you can assume that the 30 grams equals 30 milliliters. That's what we mean. The molecular weight of potassium nitrate, KNO3, is 101.11. So the first thing that we need to do is we need to convert this 30 grams to molarity, or moles. Then we need to take total volume and divide it, and that'll get us our molarity. And then you can see that the reaction is going to be KNO3, solid, goes to potassium plus nitrate. And so the KSP for this right here is going to be the concentration of potassium times the concentration of nitrate. That's how we would calculate the solubility product of potassium nitrate. And because we know that potassium nitrate is very forms a precipitate, okay? Then we can say that, it readily dissolves. It readily dissolves. Then we can say that the KSP is probably a large number. Okay, so let's go ahead and do this math. You take 30 divided by 101.11. So let me clear this because I have that calculation for you. 30 divided by 101.11 is 0.297 moles. Now assume that it's additive, and I assume that the density of the solution is 1. Why? Because let's say that 100 milliliters of water is also 100 grams of water if we assume that the density of water is 1. So 100 grams plus 30 grams is 130 grams total. But if the density of the solution is 1 gram per mil, then 130 grams is 130 mils, okay? So that's basically what I have here. We have 130 grams of solution, and that 130 grams of solution is 130 milliliters of solution because we're assuming the density is 1. If you're not given the density, you can make that assumption. Okay, if you don't have other information, you can make that assumption. If you are given the density, then you use the density as a conversion factor to go from grams of the solution to volume of solution. You guys should know how to do that based on our exercise in chapter 13. But here it's 1. So we just take 0.297 moles divided by 0.130 liters, and we see that the molarity, how much of it actually goes in solution, is 2.285. That's a big number. If we want to calculate the solubility, we can say that S squared, I mean the solubility constant, S squared, because remember, S is how much goes into solution. It's equal to potassium and to the nitrate. So S squared is the KSP. So that's basically what you see right here. So that's a typical calculation if you're given a chart like that. And you guys know how to do that based on your experience in general chemistry. The only 201 in this example right here is the fact that you multiply S times S to get the KSP, the equilibrium constant. Here's another chart. This is a more extensive chart. Let me just kind of show you what this chart is. At these temperatures, okay, these temperatures right here, this is potassium nitrate. These are the mass percent, and this happens to be the molality if you're given this mass percent, and this happens to be the concentration in terms of molarity if you're given this mass percent. This happens to be the density, and here has to do with, remember the Van Hoff factor? Hopefully you guys remember the Van Hoff factor. The Van Hoff factor is when you put a substance in water, it breaks up into its ions. Ideally, because you've got potassium nitrate has potassium ions and nitrate ions, then the Van Hoff, then the number of ions equals 2. I should equal 2. But what happens is that not everything breaks up into ions. Some of them sticks. And when they stick, then it doesn't give you a 1-to-2 ratio of substance to ions. So that number 2 is going to be reduced depending on how much of that chemical actually sticks. And so that right there is N. So delta, I believe that's the change in the temperature. I think it's a boiling point, elevation temperature, and then of course this is the refraction index. But this just gives you some data that people have collected for potassium nitrate depending on what happens. The variable before the slash is the quantity that's being measured, and then after the slash, that's the units. Okay, that's the units. Let me ask you this question. I have lanthanum iodide, barium iodide, silver iodide. And I already told you that S stands for how much of that chemical goes into solution. Okay, S is the solubility. You have a solid, and S is the amount that dissolves, that goes into solution. The fact that these numbers are small tells you that most of it stays as a precipitate. Very, very little goes into solution. This one has, this has a KSP. Remember, KSP is an equilibrium constant of 10 to the minus 12. This one has a KSP of 10 to the minus 9. This one has a KSP of 10 to the minus 8. KSP tells you the extent by which that solution, that reaction goes to products. The products in this particular case are the ions of the salt. So if I ask you, which one will have the largest solubility and which one will have the smallest solubility? And looking at these KSP, you would say, oh, the one that is least soluble is probably going to be that because that's the smallest number. So that should have the smallest S value. That should have the smallest solubility. That has the chemical that is going to give you the least amount of chemical that goes into solution. And you would also look at these chart and say, this would be first, this would be second, and this would be third. Okay, just based on KSP. And I would say, yeah, that's good reasoning, but it's not the exact reasoning. You actually have to work out the problem. And how do you work out the problem? Well, you calculate S. And how do you calculate S? Let's consider this guy right here, barium iodide. And the formula is barium and 2 iodide. Okay, sorry, 2. So that gives you 1 barium and 2 iodides. And the reason why you need to write down that reaction is because you need to keep track of how much chemicals you have in terms of the S. So this is a solid. This is 0 and 0, and then the change will be minus S. It's still minus S because there's one substance that you have in the beginning. But this, of course, is plus S, and this is plus 2S. So the KSP from here, you can just go to this. The KSP is equal to S times 2S squared. This right here is squared because you've got a 2 right there. You've got a 2 right here. So that is equal to 4S cubed. 4S cubed. So let me clear this real quick. You guys should know how to do this math type of problem. If not, you need to practice. Okay, you need to practice. You can say that the KSP, which is 1.5 times 10 to the minus 9 equals 4S cubed. We divide by 4 on both sides. We take the cube root, and that is equal to S. So if we take 1.5 times 10 to the minus 9, let me get my calculator real quick. I'm going to punch in 1.5 to the 9 negative and divide that by 4 first, and then take the cube root of that. Okay, cube root, not the square root, but the cube root. And how do you take a cube root? You raise that answer to the 1/3 power. That's how you get it to the cube root. Or if your calculator has a square root symbol and there's a 3 in front of that square root, then that's the cube root. Okay, so what I'm going to do is I'm going to use this function right here. I don't know if you guys can see that. Okay, no, you can't see that because it's a ghost, but it's a cube root function. I'm going to, in my calculator, and when I do that, I get the following. Let's see, 1.5 to the 9, enter, 4 divide. 1.5 to the 9, enter, 4 divide cube. So I get 7.2, 1 times 10 to the minus 4. That's my solubility for that. Okay, you guys should do the same thing for the lanthanum iodate, and that's going to be, you see how you get an S here and a 3S cube here? So it's going to be 27S to the 4th. Is that this one is just 2, so that's S times S. So that's just KSP, the square root of that. And so when you do that, let me go ahead and show you that work. These are the solubility. Remember I told you for barium iodate, it was 7.2 times 10 to the minus 4. Here's our answer. But when you do that for the others, solubility for lanthanum iodide is 6.9 times 10 to the minus 4. The solubility for silver iodide is 1.8 times 10 to the minus 4. So the chemical that is the most soluble is going to be the barium iodate, not the silver iodate that we thought because it had a smaller number. And the least soluble is going to be the silver iodate, which we thought was going to be the most soluble. And again, it's because these numbers are small. This is a smaller number than this, and this is the biggest number of them all. The bigger the number, the more of that chemical will go into solution. So 7.2 times 10 to the minus 4 means that the barium iodate is more soluble than lanthanum iodide that only has a solubility of 6.9 times 10 to the minus 4, which is more soluble than silver iodate, which is 1.8 times 10 to the minus 4. That's why you gotta understand what solubility means. When I say it's more soluble, it means it's going to dissolve to a greater extent. You're going to have more of these chemicals dissolving into the water and more of the ions that's going to be present. That's what more soluble is. Less precipitate, in other words. So the reason why at first glance you might make assume that this was the most soluble because this was, remember, K equilibrium is um, an indicator of efficiency. Well, 3.1 times 10 to the minus 8 is a bigger number than 6.2 times 10 minus 12. So you would expect silver iodide, that reaction, to be more efficient. But it's not, because this thing only breaks up to 2 ions, whereas this breaks up to 4 and this breaks up to 3. You actually have to work out the math. Now, if all of these were the same, if it gave you the same number of ions when you put it in solution, just look at the KSP, because the math is going to be the same for all. The fact that you have different number of ions for each one, you actually have to work out the problem. Okay, so if the same number of ions form between two chemicals, then the greater the solubility, the greater the degree of a substance dissolved in solution. Suppose instead of silver iodate, I also have, let's say, what's a good one that's mono ionic. Let's say that I have barium iodate and we have lead iodate. Okay, and I tell you that lead iodate has a KSP of somewhere in the order of 2.0 times 10 to the minus 8. Well, that you can compare readily with this. Why? Because this thing forms 3, this thing forms 3. The math is the same, and so when you work out the S is going to be bigger for this number right here, because that's going to be a bigger KSP. So you can take shortcut if you understand the chemistry that's going on. Okay. So let's take a look at the solubility rules. What is it used for? Well, it was used for when you guys were in chemistry 200. Tell you whether a chemical is going to dissolve or not dissolve, whether a precipitate will form. And here in Chem 201, we take the solubility rules and extend it, because now we can calculate how much of it dissolves. So the solubility rules are the following. It tells you that when you have a nitrate salt, when you have a chlorate salt, when you have a perchlorate salt, or when you have an acetate salt, no matter what the cation is, it dissolves in water up to the solubility limit. What is the solubility limit? The solubility limit is, like, for example, potassium nitrate. You can dissolve 30 grams in 100 milliliters. That's the solubility limit, but a lot of it dissolves, okay? Whereas chemicals that are not soluble in water, you put it in water, it looks like nothing's gone in because you still see a precipitate in the solution. That's what the solubility table gives you. That's what the solubility rule gives you. Um, when you have alkali or ammonia as the cation, they will always be soluble up to the solubility limit again. On the other hand, when you have halogenated anions, chlorine, bromine, and iodine, then they're soluble except when the cation is silver, mercury, or lead. Sulfates, if you have a sulfate anion, then they are soluble except when you have barium, mercury, and lead. So the solubility rules tells you generally what is soluble, and then it tells you the exception. Here, these things are insoluble: carbonate, phosphate, hydroxide, except here, carbonate, phosphate. If you have alkali, group 1, or NH4, because this takes precedence over anything else, it will be soluble. Anything with group 1 or ammonia will always be soluble, even if you have carbonates or phosphates. But in general, they tend to be insoluble. That's the solubility rules. Hydroxides are soluble except when you have alkali, ammonia, calcium, strontium, and barium. Calcium, strontium, and barium are what we call heavy group 2. Barium, strontium, uh, barium, strontium, and calcium are in group 2, 2A, but they are heavier, have a higher molar mass in general. That's why we call them heavy group 2. So that's the solubility table. And the reason why I show you this is because a lot of times you will be mixing two chemicals And one chemical has one ion, another chemical has another ion, but how do you introduce those ions? Okay, you introduce those ions as a salt in a double displacement reaction. And the reason why they dissolve is because it's readily soluble in water. That's what the solubility rules tells us. So let me try and demonstrate that in the next few examples. Okay. By the way, in general, a molar solubility of 0.01 or greater for a substance is considered soluble. So when something in the order of 0.01 molar or higher goes into solution, then it's considered soluble. If it's less than 0.01, then it's considered insoluble. That's what the solubility rules tell us. So let's take a look at calcium phosphate. And again, this is a precipitation reaction where we get calcium phosphate, but we don't write it that way, okay? And the other thing you need to remember is that the phosphate is insoluble. And that's what you see here by this S. So here's how we would write that reaction again as a dissolution. Dissolution. Dissolution, meaning it's going to dissolve. Calcium phosphate goes to 3 calcium and 2 phosphate. And the question is, will, if we have a certain concentrations of the calcium and the phosphate, will it all dissolve or will we see a precipitate depending on how much we have? So to answer that, we need to calculate this reaction quotient Q. Remember, Q is an indicator of whether the reaction is going to go in the forward direction or the reverse direction. If it's going in the forward direction, that means it's going to be soluble because the calcium phosphate goes to calcium and phosphate. So in the forward direction, it's dissolving, it's soluble. If it's going in the reverse direction, then it's insoluble. It will precipitate out. That's what it means. And how do we know if it's going in the reverse or the forward direction? We look at Q relative to KSP. If Q is less than KSP, then it's going to go in the forward direction. In other words, it's going to be soluble. It's going to go in solution. You shouldn't see any precipitate. On the other hand, if Q is greater than the KSP, then you're going to start to see it's going to be insoluble. You're going to see more of the precipitate forms. So again, it's this idea of we're not at equilibrium. We want to know how to get to equilibrium, and that's what Q serves. It gives us an idea about that. So Q now is called the ion product because remember, this right here is KSP is equal to calcium plus 2 squared times phosphate, sorry, that's 3, minus 3 squared. These are multiplied by each other. When you do a multiplication, that's a product, okay? What's the product of 5 times 6? Okay, that would be 30. What's the product of 7 times 3? So the ion product is you're taking the ion concentration and you're multiplying it against each other raised to its coefficient in the balance equation. That's why it's called an ion product. They're very clever in naming these things. Anyway, let's take a look at this right here. Again, this is what I just showed you. It's an indicator of whether it's going to dissolves this way. In other words, it's soluble. It forms a precipitate this way. In other words, it's insoluble. Clear that. So it's unsaturated when Q is less than KSP, and it's not going to form a precipitate. It's going to dissolve here. It's saturated. It's oversaturated, and that amount that is above the solubility is going to start to form a precipitate. So here's the question. We have barium iodate forms when 6.5 grams of barium chloride is dissolved in 0.500 liters of 0.33 molar sodium iodate. So here's how you would visualize this problem. We have a test tube here, and we have barium chloride. And we have 6.5 milligrams here. And we have a second test tube. And here we have sodium iodate. And we have 0.033 molars here. And we put both of them together into a bigger solution. And this total volume now is 0.500 liters. In other words, 500 milliliters. And the question is, when you have these two chemicals mixed in, will you get a precipitate or is it going to be dissolved? That's the question. Now, don't make this any harder for yourself. You might overanalyze this. You might say, okay, I've got 0.033 molar sodium iodide. So I need to calculate how much iodide is in this solution based on the KSP of sodium iodate. And here I've got barium chloride. I got 6.5 milligrams of that. And I need to figure out how much of that is actually barium based on the KSP of barium chloride. That's where the solubility rules comes in. I tell you that anything with a group 1 is 100% soluble. So you can say that the amount of iodate in the sodium iodate solution here is also 0.0133 molar. That's the iodate concentration. Why? Because it's 100% soluble according to the solubility table. Therefore, you don't have to calculate that value. Everything will dissolve, and that's how much iodate you would get. Here, the barium chloride, the chloride, salt, everything's soluble except if you have silver, mercury, or lead. So this will be 6.5 grams of barium in that particular, or barium chloride in that solution. So your job is to figure out the concentration of barium from 6.5 grams of barium chloride. And you know the iodate concentration because that's already given in the problem. And then that'll be your concentrations of your ions. You multiply them against each other based on the mass action expression, and then see whether that Q value is bigger or smaller than the KSP. So this is what it looks like. Okay, this is the reaction. For barium, 6.5 grams is going to be 6.2 times 10 to the minus 5 molars. I'm not going to do that math for you because you guys should know how to do that. You take 6.5 milligrams of barium chloride, figure out the molar mass of barium chloride. That'll get you the moles of barium chloride. And then you know that for every 1 mole of barium chloride, you have 1 moles of barium. So the moles of barium chloride is equal to the moles of barium. And divided in 0.5 liters, that's your molarity. And then the iodate is just 3.3 times 10 to the minus 2. And if you multiply that against each other based on this mass action expression, but for Q, you get this number, 6.8 times 10 to the minus 8. And we said that the KSP for this particular chemical is 1.5 times 10 to the minus 9. You can already see that Q is bigger than the KSP, which is 1.5 times 10 to the minus 9. Q is 6.8 times 10 to the minus 8. So the reaction is going to form a precipitate. Okay, the reaction is going to go in the reverse direction because Q is bigger than the KSP. And a precipitate forms. So that's how you would solve that problem. Okay, let me finish today's discussion with the common ion effect, and then we'll continue on Monday because your quiz 2, which covers equilibrium, isn't this weekend. It's next weekend. Okay, and probably Monday we'll wrap up this particular section. So common ion effect basically means that you've got a reaction. This is your reaction. You got silver iodide in equilibrium with silver plus iodide. You guys will do the common ion effect a lot in experiment number 3. Okay, so it's in equilibrium. And the question is, okay, I have a solid here, and this is 0 and 0, and then you can see how much of it goes into solution. But suppose I add to this silver iodide some sodium iodide. See how sodium iodide has a common ion to this reaction that we have, the common ion's iodide. That's why it's called the common ion effect, because there's a common ion that's involved in this reaction. Well, that means that if I introduce iodide, sodium iodide into the solution, and the iodide is going to affect the mass action expression, and it's going to cause this number to be bigger. And according to Le Chatelier's principle, if you put a stress on the product side, the reaction is going to shift to the reactant. And so you would get more precipitate based on this common ion effect. And so that's exactly what's going on. We add more sodium iodide, and you're going to get more precipitate going, crashing out of solution. Remember that in this initial reaction, you've got silver in solution, you've got iodide in solution, not very much of it. But by introducing more iodide, you're going to exhaust more silver because a precipitate has to form. So the silver concentration is going to go down, but that gives you that's the reason why you have more precipitate. That's the common ion effect, okay? And again, you might say to yourself, well, if I introduce sodium iodide, don't I have to figure out how much of the iodide is going to be in solution? Because isn't sodium iodide a solid? Again, it goes back to the solubility rules. Sodium iodide is 100% soluble in water. So whatever concentration you have of sodium iodide, that'll be the concentration of sodium, that'll be the concentration of iodide, okay? That's an important distinction that you guys have to remember. So that's the silver, that's the common ion effect. And I'm going to skip this movie, but again, this is the teeter-totter analogy. We've got an equilibrium here of silver and iodide. We add more sodium iodide. According to Le Chatelier's principle, you're putting a stress on the product. That means the reaction is going to shift to the left. You get more precipitate forming. You can see that in the mathematics. You've got this Q value, silver and iodide. You increase I. If you increase I, that means that the Q value is going to be greater than the KSP, and that therefore, in order for Q to get back to equilibrium, the reaction has got to move to the left, that you see here. And this reaction moving to the left means you have more precipitate. The math and this teeter-totter analogy sings the same song. This problem right here is a typical problem that we've covered in our previous discussion. What is the solubility? And remember that you need to know the difference between the solubility, which is how much of that solid goes into solution, which we call S, and the solubility constant, which is an equilibrium constant. So here you're given the solubility constant, KSP. And again, the SP stands for solubility product. In this particular case, it's 1.1 times 10 to the minus 12. Generally, when things are insoluble, you're going to get very, very small numbers, meaning that it doesn't go very much into solution, it stays as a solid. So we have the solubility constant as 1.1 times 10 to the minus 12. So this problem is pretty straightforward to solve because you know that from the ice table, you're going to have a solid going to solution. So that's minus S that you see here, plus S plus S. And what we have is the equilibrium equation. And this is fairly easy just because one solid breaks up into two ions, so it's just S times S. If it breaks up into four ions, and you'll see an example of that later on, and how does it break up into four ions? Maybe you have silver phosphate. And silver, there's going to be 3 silvers for every 1 phosphate because silver's plus 1, phosphate's minus 3. So it breaks up into 4 ions. Okay, so the math becomes a little bit more complicated and you guys will need to know how to solve those types of problems. But this one's straightforward. You see that S squared is equal to 1.1 times 10 to the minus 12. You take the square root of 1.1 times 10 to the minus 12, you get the solubility. When you put copper iodide into water, the amount of copper ions and iodide ions is going to be 1.05 times 10 to the minus 6 molar. It's a small amount, but it can still be detected, especially if you've got instrumental techniques. So in other words, even though chemical is insoluble, you still get a small part of it going into solution. So that's what you see from that problem. Now, suppose you have sodium iodide. Now, sodium iodide is NaI. And you guys know from the solubility rules that all sodium salts, group 1 salts, are soluble up to the solubility limit. And how can you determine the solubility limit? Well, maybe you have a graph from what I showed you last time, or we tell you what the solubility limit happens to be. We say that it's for every 100 grams of water, about 20 grams of it dissolves. Well, if you're given 20 grams of it in every 100 grams of water, then you can calculate the molar solubility. But this concentration, 0.05, is way below that solubility limit. In other words, you take sodium iodide and you have 0.05 molar. All of it is going to sodium ions and iodide, iodide ions, iodide's I minus. Okay, so you can assume that the initial concentration of your iodine is going to be 0.05 molar. That's the key. If you forget that, then you're going to solve this problem totally incorrect. So that's what you put in the initial line right here. Okay, that right there is critical. Why? Because it's a common ion. It's a common ion effect. So before the reaction starts, you assume that that iodine is present. Now the math becomes super easy. Why? Because look at this right here. You still work on the ice table, but now the equilibrium concentration is 0.05 plus S. And so when you set up the math, you're going to get this right here. Copper times iodide equals 1.1 times 10 to the minus 12. Still, that's your fundamental equation. But now this part right here is the iodide concentration. And what you need to do is make that assumption criteria that since this number is so small, not much of it goes into solution. If not much of it goes to solution, then it's not going to add very much to 0.05. That's the key. If it doesn't add very much to 0.05, then that simply means that your equilibrium concentration is also 0.05. That's what we have right here. We can assume that S is very small compared to 0.05. That simplifies the math because now you don't have S squared. You just have 0.05 times S. And so if you take 1.1 times 10 minus 12 and divide by 0.05, then you get 2 times 10 to the minus 11. That's just S. So you can see how it simplifies the math because now you make that simplifying assumption, that is that S is very small compared to the initial amount that you have, and then you don't have to worry about that term. And then to validate your assumption, you can see that 2 times 10 to the minus 11, which is S, if you subtract 0.05, if you take 0.05 and subtract 2 times 10 to the minus 11, it's still essentially 0.05. So your assumption is pretty much valid. So you can see that when you have a problem like this, when you have a problem where you have common ion, take advantage of it because the math will be much easier than if you had the regular problem. And you see that in acid-base chemistry as well. Okay, so these are your solutions for the first part. The solubility is 1.05 times 10 to the minus 6. Okay, the concentration when you put it into solution is 1.05, or the amount that dissolves is 1.05 times 10 minus 6. The copper ion and the iodide ions, 1.05 times 10 minus 6. But when you have a common ion, the amount that dissolves now is 2 times 10 to the minus 11. In other words, the equilibrium going to the products is hindered by Le Chatelier's principle. You now have iodine in there. It's going to cause the equilibrium to shift to the left, more precipitate. It's going to inhibit the dissolving process, and therefore your solubility decreases drastically. Okay, so everything sort of paints the same story. You gotta understand the results here in terms of what we've learned in the past. That is Le Chatelier's principle. So let's move on. Here's another problem. We have, what is the solubility of calcium fluoride, 0.025, sodium fluoride solution. So in this particular case, we've got, this is pretty straightforward. We've got 0.025 as the concentration of calcium fluoride. What is the solubility? 0.025 sodium fluoride solution, KSP 6.2 times 10 minus 6. In other words, if you have this type of problem where you're given the concentration of calcium fluoride, you need to figure out whether or not this thing is going to be soluble or not. So here we have this right here. We have 0.025 times 10 to minus 2. That's basically the concentration that you have. The remember that you have, let me sort of draw a picture for you so you can see what's going on. In here, you're putting some calcium fluoride. And make sure you write the correct formula, because if you don't have the correct formula, your setup is going to be incorrect. And then to this right here, you've got sodium fluoride, NaF. And that's going to be soluble. Why? Because sodium is a salt that's soluble. So there's a question here. So because a common ion in the last equation happens to be a reactant, Le Chatelier, it's actually in the last equation, let me go back to that real quick. Okay. Here, it's actually a sodium. Let's see the question. So in the last equation, what happens to the reactant? Le Chatelier principle still forces the reaction left, basically, even though it isn't involved in the reaction technically. It is involved in the reaction technically because iodide is involved in the reaction. And so what that means is that it's going to cause a stress on the product side. How would you introduce iodide into the solution? You can't just take iodine ions in a test tube. You have to introduce it as a salt. And then you assume that the sodium is a spectator ion, that it doesn't participate in the reaction. So the iodide is introduced to this reaction as a salt. Now the iodide goes in and deals with the chemistry of copper iodide. And now, because of Le Chatelier's principle, you're applying a stress on the product, which causes the equilibrium to shift to the left. That's what's going on. So technically, the sodium iodide the sodium is a spectator. That doesn't get involved in the equilibrium, but the iodide is directly involved, because if you look at the mass action expression, it's in the mass action expression, the iodide. Okay, so it does affect that equilibrium. Hopefully that's clear. Okay, here, the same thing. You're introducing sodium fluoride. The sodium is a spectator. How do you know it's a spectator? Well, it's not in the mass action expression, but the fluoride is. Okay, so when you write the mass action expression, you'll see that this is going to be equal to calcium times fluoride squared. And you're introducing fluoride in this reaction via sodium fluoride. And you got to know that the amount of sodium fluoride you see in the next example, that's not always true, that when you put in a salt, maybe you have to deal with a secondary reaction. But this one, no problem, because salts are soluble in water up to the solubility limit. But when we have a 0.025 molar solution, you can assume that that's pretty small, that all the sodium fluoride will go into solution. Okay, so put in sodium fluoride, the concentration of this is 0.025. That means that the fluoride ion in here is going to be 0.025 molar. Okay, that means, and that's your initial concentration as well. And so what happens is that some of the calcium will dissolve, a little bit of the fluorine will dissolve, and the question is, how much of it dissolves? That's what this question is. What is the solubility of the calcium fluoride when you have a common ion, fluoride ion, in that solution via sodium fluoride? So again, we solved this problem. We have this, but now pay attention. You have 2s here. Why? Because of that stoichiometry right there. And then you can make this assumption that 0.025 plus 2s, my s and my 5 looks the same. This is a 5, that's an s. And you can assume this is negligible. Why can I make that assumption? Look at this number. That's 10 to the minus 8. when you have a number like that, that means not very much of it goes into solution. So you can make that assumption. Okay, you can make that assumption. And this now becomes 0.025. So when we solve this problem, we get this right here. We assume that that's negligible. We just have S times 0.025 squared. We just solve this problem. Again, you can see how much easier this problem becomes because we can make that simplifying assumption. Okay, we don't have to deal with this term anymore. We can just say that that's negligible. So again, that's another example that I want to illustrate with you. And here's the assumption that we have. If you take away 2 times 9.92 times 10 to the minus 5 from 0.025, it's still essentially 0.025. Okay, so that's our solubility, by the way. Yes. And remember that this was our assumption right here. You can always validate your assumption by plugging it in to this equation right here where you made that assumption and see if it's true. 0.025 plus twice 9.92 times 10 to the minus 5. And if it's still essentially 0.025, then you're good. But if it changes, then you need to do a second iteration. Okay, let's take a look at this problem right here. This is one that when you introduce a second chemical, it's not soluble. So these are two insoluble salts put together. This one's a lot tougher problem, but it's not that difficult. Again, you have to play the math game, and I'll show you how to set this up. So we've got lead sulfate and strontium sulfate. They both are insoluble. How do you know? Well, go back to the solubility rules. It tells you that sulfate salts are insoluble except if you've got group 1 or ammonium, then they're soluble, because anything with group 1, sodium, lithium, potassium, or ammonium is always 100% soluble, no exceptions. That's from the solubility rules. But if you got any other type of cation, then it's insoluble. And that's what we have right here. Lead sulfate and strontium sulfate. In fact, I tell you what the KSP is. It's 1.6 times 10 to the minus 8 for lead sulfate and 2.8 times 10 to the minus 7 for strontium sulfate. So you actually have to deal with two equilibrium. Okay, so how would we solve this? Well, here's what happened. Let me kind of draw you a picture of what's going on here. Okay, so you're putting in lead sulfate and you're putting in strontium sulfate, and you're going to get these two type of solids, and one of them is going to produce lead and also sulfate, and the other one's going to produce strontium and also sulfate. So both of them produce sulfate. But the problem is that sulfate is a common ion for both equilibrium. So it's going to affect its neighbor simultaneously. How do you solve that? Well, you have to account for the fact that sulfate is coming from these two reactions, and therefore you have to put it in the math. So let me show you how that's done. So these are the two reaction, lead sulfate and strontium sulfate. So this is the mass action expression. Pretty straightforward. It's just concentration of lead times sulfate times concentration of strontium times sulfate. Okay, but this right here comes from this and likewise here. So we have to take that into account. How do we do that? Well, here's what we need to do. Okay. Oops, sorry. We have to solve this as a math problem. We can let X be lead, ion concentration. We can let strontium be Y. But remember, when one of these dissolve, it's going to form equal, like if lead dissolve, it forms an equal amount of lead and sulfate. When strontium dissolve, it forms an equal amount of strontium and sulfate. So what is the sulfate? It's going to be X plus Y. It's going to come from the equilibrium from both. That's something you just have to sort of recognize from the chemistry. Again, if you understand the chemistry, then you will know how to set up the math problem. That's why you have to be exposed to a lot of these types of problems so that it doesn't phase you when you see a question like this in a test or a homework problem. So now we have this, and now we can set up the math. Let's take a look. See, this equation right here is just that. It's just this one at the bottom. It's lead, this is lead, and this is your sulfate. So the lead concentration times the sulfate concentration equals the KSP, 1.6 times 10 to the minus 8. This equation right here is just this equation on top. It's the strontium, there's a plus 2 here, times the sulfate. But remember that the sulfate now is going to be, that's why I have X plus Y right here, is going to come from both reactions. But this is simply a math problem. It's going to be this thing, you always put the bigger number on top, that way you don't have to deal with fractions, okay? I always like to put the bigger number, 2.8 times 10 to the minus 7 on the numerator, 6 times 10 to the minus 8 in the denominator. It really won't make a difference when you do if you switch both, but now you're going to be dealing with decimal points rather than whole numbers, okay? When you take 2.8 times 10 to the minus 7 and divide it by 1.6 times 10 to the minus 8, you get 17.5. I'd rather deal with a number like 17.5 or the reciprocal of 17.5. So that's my rule of thumb in terms of making the math easier for me. I always put the bigger number. It's just like the, remember the methods of initial rate? When we did those problems, I always told you to put the bigger rate constant on top and the smaller one on the bottom. That way the math is more visible. It's much easier to see a number like 4 rather than 0.25, which is the reciprocal of 4. So that's just a strategy I have whenever I solve math problems and we have these things. So this is essentially what we have. We have these two will cancel because X plus Y in the numerator and X plus Y in the denominator are going to cancel out. And so what you have is just X over Y equals this 17.5. And isn't that an easy math problem to solve? X is just 17.5Y. Okay, and so when we do this, let me clear this for you so that you guys can see. When we do this, then we can just make the substitution here. Okay, we can make the substitution that we can take this and plug it in here and then solve for X. And when we do that, what we get is the following. Okay, we make the substitution right here. We do the math. I won't do the math for you. You guys can just follow along. And so we get this value. X is 2.94 times 10 to the minus 5. What exactly is X? X, we said, was going to be defined by the lead concentration at equilibrium. So that's the lead concentration at equilibrium. That's 2.94 times 10 to the minus 5. We can now take this number, plug it in here, and solve for Y. And when we do that, we get Y equals 5.08 times 10 to the minus 4. This is just an algebra problem. Okay, it's an algebra problem, but it's set up based on your knowledge of chemistry. And you got to recognize that, yeah, this is a common ion effect, but unlike the previous problem, you have to solve the contribution of sulfate from the other salt because it's not a soluble salt. Okay, so when we have both X and Y, now we can calculate the sulfate concentration, and that's just X plus Y. Let me clear this for you. Okay, so here it is right here. This right here is 5.08 times 10 to the minus 4 plus 2.94 times 10 to the minus 5, and that's your sulfate ion concentration. You can always go back and plug in these values to test whether or not it equals 1.6 times 10 to the minus 8. In fact, that's a rule of thumb. At the end, when you get an answer, go back, take those numbers at equilibrium, plug it into the mass action expression, and double check that you are getting the equilibrium constant. That's how you check your math. Okay? If you take this and this, those two should equal 2.8 times 10 to the minus 7. That's a good way to double check your work. You did all that work coming up with these answers, and maybe you made a mistake along the way, simple arithmetic mistake, you punched in the wrong value or something. This will tell you whether those numbers are valid. Okay. So in terms of the chemistry, everything here looks good. You have your answers and you're pretty much done. You've answered the questions. What are the values of sulfate, lead, and strontium in a solution at equilibrium with both substances? You've answered the question. There's nothing more to add. Those are the answers. So let's move on to this one. It's a very similar problem, except it's a little bit more complicated. Why? Because take a look at the formula. It's zinc iodate. IO3 is, let me back up. Okay. Uh, zinc iodate. It's a parenthesis, not a bracket, squared. So you can see that there's a squared term in the mass action expression, but not to worry, both of them are squared. Okay, both of them are squared. So again, you approach this problem the same way. I'm using M and N this time because you guys know from math, the letters are just variables. And you can change it to X, you can change it to Q, you can change it to G, whatever, and it just represents a number. Okay, it's just from algebra. So I'm using M and N in this particular case. I could have used X and Y. Doesn't really matter, but it's just substituting for some numbers. So the iodate is going to come from both chemicals. The M here is coming from the zinc. That means that the N is coming from the strontium. And so what you have, let me clear this real quick. Okay, are these two, oops, equilibrium. So what is the math that you need to do? Well, take the, let me see, which one is the bigger number? 3.9 times 10 to the minus 6 is the bigger number, and I'm going to make that over the smaller number, minus 7. So this is equal to the zinc, and the zinc is M times 2M plus 2N squared. And then the smaller value is the strontium, and that's N. That's 2M plus 2N squared. This term cancels. It's just M over N equals whatever that ratio is. The rest is math. Okay, and so that's what you see right here. Let me clear this for you. And you guys can solve that. And if you do the math and just go through, what you will see is that N equals times N times 1.1818 times 10 to the first equals M. You make the substitution, and those are the concentrations of your strontium, your zinc, and your iodate. Check it out, okay? But the rest is algebra. Practice these things. The algebra is not so difficult once you set it up correctly, okay? So that's your answer. So try this extra credit homework. Try and turn it in by Wednesday. This one's a little bit tricky, okay? Let's try this. I'll put in Canvas a place where you can deposit your work. You've got silver iodide and lead iodide. This one's not so easy. Why? Because this is this KSP is equal to silver times iodide. Okay, this one right here is equal to lead times iodide squared. So the x plus y in terms doesn't really cancel because you've got a square term in there. But it's a math problem, so once you set it up, so that's why I'm giving you this as an extra credit. Figure it out. For those of you who really like math, you can figure this out. You probably could make some simplifying assumptions. And the reason why you could make simplifying assumptions is look at this. Look at the equilibrium. It's 8.3 times 10 to the minus 17 for silver, and it's only 7.9 times 10 to the minus 9 for lead. So in there, you can see that the silver contribution to iodine is so much smaller compared to the lead contribution to iodine. So use that and what you know about what we've talked so far to solve this problem. Okay, so it's an extra point bonus if you can solve it, and it's basically just a math problem. Set it up correctly. So let me move on, and I'll put this in the announcement page in Canvas so that you guys can see it again, but it's basically in lecture notes 15.04. Okay, so this is another problem, and this particular is calculate the molar solubility of cerium iodate in pure water. What is the concentration of sodium iodate in solution necessary to reduce the cerium concentration in a saturated solution of cerium iodide, iodate, IO3 is iodate, okay, IO3 minus iodate. Um, in a saturated solution of cerium iodate by a factor of 10. So that's the second part. Let's solve the first part. The first part is pretty easy, okay? What is the molar solubility? Well, you know that cerium, if you do this enough times, you're going to see that this is KSP is equal to cerium iodate squared. How did I get squared? Cube. How did I get cube? There's a 3 right there. Okay, so this is S. This right here happens to be 3S cubed. That's 27S to the 4th. And that's equal to the cerium. And we've solved these types of problems in the past. Let me just show you how that works. Let me clear this for you. Okay, so you can see that it's 27S to the 4th. You solve for S, that's 1.86 times 10 to the minus 3. That's how much of cerium iodate that we would solve if you put it in water. And then we use that answer. We use that answer to solve the second. What is concentration of sodium iodate in solution would be necessary to reduce the cerium concentration in a saturated solution by a factor of 10. Okay, so when we reduce this by a factor of 10, all we've got to do is divide it by 10. That's what we see right there. To reduce cerium by a factor of 10, we divide that number by 10. Now that happens to be our cerium, which happens to be 1.86 times 10 to the minus 4. It's 10, a factor of 10 less than that. Now we can plug it into our mass action expression, this new value, and we can calculate the iodate concentration because that's the amount of sodium iodate we would need. So when we do that, we get iodate cubed, and you might ask yourself, well, why don't I put 3S cubed? Why can't I do that? Well, 3S is the iodate, okay? The iodate concentration in solution. That's the total. That's 3S equals the total iodate concentration in solution. It just so happens that 3S comes from the fact that this chemical, when it dissolves, spits out 3 iodate. So you got to make sure that that's clear in your mind, because you can't put 3S in there and make it more confusing for yourself. Put the iodate because that's the equilibrium concentration. Yeah, that extra credit's due before class so that I can go over it. Okay. I'll put the deadline when I put that in the announcement. So that's your iodate concentration. That's the equilibrium concentration over here. And all we got to do is solve that problem. You know what the cerium is. You know what the KSB. We can calculate the iodate. That's the total concentration at equilibrium. Now, the total concentration at equilibrium is going to be the iodate. That's the 3S from the cerium dissolving plus the iodate from the sodium iodate. The question is, what concentration of sodium iodate is needed? So this problem is not finished. That's just the total concentration at equilibrium. What that is equal to, 1.98 times 10 to the minus 3 is equal to 1.86 times 10 to the minus 4 plus the amount of iodate from the sodium. So this is what you need to do further on. So this right here is equal to 1.198. That's that total right there, minus the amount of this guy that dissolves, the 1.86 times 10 to the minus 4, because that's the contribution from the equilibrium from cerium iodate. Okay, you're getting iodate from two sources, the cerium iodate and the sodium iodate. And the question is, what is the concentration of the sodium iodate that you need? So that's why I put that number here. We have this number that's from the fact that the cerium iodate will give you 1.86 times 10 to the minus 4 cerium, 1.86 times 10 to the minus 4 iodate, three of those. So we just finished this math, and that is the concentration of your sodium iodate that you would need to cause this to precipitate out. And how would I check that? I just go back in here and say 3.2 times 10 to the minus 10 is equal to this concentration of cerium, 1.86 times 10 to the minus 4 times this concentration, 1.14 times 10 to the minus 2 plus 1.86 times 10 to the minus 3, 4, 3 times. Why 3 times? Because of that right there. And then we cube that. So if you solve that math, what you should see is that that math will give you, if you solve this right here, that is going to be equal to that. That's how you double check your work. Okay. So if you're pressed for time, then yeah, you're not gonna have time to double check your work. But if you want to see if you're correct, always go back to the end and look at the fundamentals. Are the answers that you have, when you plug it into the mass action expression, is it equal to the KSP? It's basically how you would double check your work. So this is the correct answer for that problem. Okay. So yeah, we had a lot of math, and I told you, equilibrium, there's a lot of math. Acid base, there's a lot of math. So if your head hurts when you do a lot of these, it's actually a good remedy. It's brain exercise. Okay. Let's take a look at this. We're gonna change gears a little bit, and we're going to look at qualitative analysis. Qualitative analysis is the chemistry of figuring out what's there. Okay. Qualitative means what is present, what chemicals are involved. Quantitative is the question of how much. In my analytical chemistry course, it's called quantitative analysis. And that's because we always want to figure out how much chemicals we have in the solution we're analyzing. We already know what we have. We're trying to figure out how much we have. Okay, and you find out that quantity is a very important science, because we want to know how much pollution we have. We want to know how much bacteria we have. We want to know how much basically virus we might have in our system. So we're always looking at number, but you have to first know what you're looking for. That's qualitative analysis, and that's what we're looking at in this particular section. So when I was taking general chemistry, because I went to San Diego State for my undergraduate degree, and second semester general chemistry, that's what you guys are taking here. In lab, we had like 4 weeks. It's like the first month, basically, where we had to do an experiment, and it was practically half our grade. And the experiment that we ran was, you're given a bunch of test tubes, and they've got certain ions in there, and it's up to you to figure out chemical scheme to figure out what are the ions present. And you're not put in there in the lab room blindly. You know your chemistry. You know what tests to do in order to test for silver. You know what tests to do in order to test for like barium or some other ions, lead. Okay, so you use that knowledge and go through a series of tests to figure out what ions you have in your unknown. And then if you get it correct, then you get a good grade. If you mess up, then you don't get a good grade. But this is basically what we're doing. And we're using what we learned from chapter 15 to write up a scheme. So here we have a bunch of test tube and we do a bunch of tests, and depending on whether we get a precipitate or not, we know what possible ions we have. Okay, so that's what qualitative analysis is. And so in this particular case, here's, let me just make sure that I have this. Yeah, here's the different types of groups. We have this purple, orange, yellow, green, and blue. And they are in a family of ions that react very similarly based on their solubility. So if you take an unknown test tube, and the first thing that you do is add silver hydrochloric acid, 6 molar hydrochloric acid, then you guys know already from the solubility rules that if it has silver ions, if it's got lead ions, we don't give you mercury. Mercury is a poison, okay? But if you did have mercury, it's going to precipitate out. Why? Because the solubility rules tells you those salts are insoluble. So that's essentially what happens right here. You're going to, if you take that test tube that has a solution in it, and it doesn't look like it's got a precipitate, it's just basically a test tube that looks like this, and you don't know what's in there, you add a little bit of hydrochloric acid, drops of hydrochloric acid, and you see a precipitation, then you know you've got a positive test for silver, lead, and mercury. If you want to take that precipitate and do further analysis, then you can distill it down to whether you have silver, mercury, or lead. But we won't go there. That's for another class. Now, what will happen is that'll precipitate out. What you do is you decant the supernatant. The supernatant is basically the liquid above the precipitate. And then you put it into a new test tube. And you don't know if you still have ions in there. So what do? You run a second test. In this particular case, you add hydrogen sulfide in, okay, acidic conditions. That's why you have HCl in here. You've already removed the silver, the mercury, the lead. So adding HCl to this solution is not going to cause further precipitation. That's what this was. You removed it through the precipitation. So by making this solution acidic and then adding H2S, look what will precipitate out. These sulfide salts are insoluble under acidic conditions. And that would be the orange group. What you would get a precipitate of is, let me blow this up so that you guys can see this better. You would get the silver, bismuth, cadmium, lead, mercury, but we already know that lead, mercury, and silver will be in here, okay? We figured that out from the first test. So we're really testing for copper, bismuth, cadmium, arsenic, antimony, and tin. If you get a sulfide salt from that, then you know it's present. What you want to do now is you want to take this precipitate that forms. What happened here? We want to take this precipitate that forms, decant it. I'm messing up my, let me go back to this. Okay, my iPad doesn't like the zoom section. You get a precipitate over here. If the sulfides are insoluble, you basically separate it by decanting the supernatant, and then you can test under basic conditions. That's why you add hydroxide, okay? And add hydroxide, and under basic conditions, the aluminum, the iron, the chromium, the zinc, the nickel, we already test for no, that's cobalt, manganese, and iron will precipitate out. So under acidic conditions, these sulfide salts will precipitate out. Under basic conditions, this sulfide salts will precipitate out. Okay, you change the pH of the solution to precipitate one group versus another group. And then if something precipitates out, again, you get a solid in the bottom of the test tube. You decant that. You only test the supernatant because the precipitate tells you the presence of these guys right here. Now that you have the supernatant, you're going to add a little bit of ammonia, and then you're going to add this lead biphosphate, HPO4. Okay, it's -2 because phosphate, PO4 is -3. So when you put an H there, which is a cation, it reduces the charge by, increases the charge by 1. So it goes from -3 to -2. And that chemical is not necessarily called hydrogen phosphate. It's better known as biphosphate. So when you add biphosphate in here, you get the phosphate salts. And then anything that doesn't dissolve, you've got ammonia, sodium, lithium, potassium. Okay, those are the salts. And what would you do in order to test for that? You could probably do a flame test if you really want to do, you want to figure it out. But that's the qualitative scheme that you use to identify different salts. These days, we don't want to give you those ions. Why? It's, well, they're kind of poisonous, and we always are concerned about our safety. So we could give you. There was a scheme that I generated for Chem 200. Remember that my name is in the Chem 200 lab manual because I was only one of two professors when Miramar started their chemistry program. Well, I sort of wrote that in there, and it's actually taking household chemicals like sodium chloride, like Epsom salt, magnesium sulfate, like plaster of Paris, and doing a qualitative analysis on that. But here's another scheme right here. If you have these in a test tube and you add water, then these things will not be soluble. These things will be soluble. And we can take this further and do further tests. So you should be able to read a qual scheme like this. And if I give you a test tube and I say, okay, you have this solution, you're adding water, you get a precipitate out, okay? To that precipitate, you isolate the precipitate, you add hydrochloric acid to it, and you see bubbles. Um, and then you add, you see that the solution is neutral. Well, when you see bubbles, you should be able to say that, oh, my unknown contains calcium carbonate. Okay. In fact, any carbonate chemical will produce bubbles because CO3 in the presence of acid will give you carbonic acid, and carbonic acid is very unstable. It actually forms water and CO2, which is your bubbles. It's just the chemistry that happens whenever you have carbonate ions. Okay, that's why if you take baking soda and you add vinegar to it, you see bubbles. That's carbon dioxide. So that's a qual scheme. So make sure you understand that. Here's an example of a solution contains 2 times 10 to the minus 4 silver and 1.5 times 10 to the minus 3 lead. If sodium iodide is added, will silver iodide or lead iodide precipitate first? You actually don't need to do this problem. You can just go based on, well, let me just see. This is 1 iodide and this is a 2 iodide right here. So you actually have to do the math. If you had, if they both produce 2 iodide or 1 iodide, then you can just look at the KSP. But here, one chemical produces 1 iodide, the other chemical produces 2 iodide. So you actually have to solve the math. So this is how I would solve for it. I would do the silver first just because it has some very, very small equilibrium, 8.5 times 10 minus 17. So again, it's going to be common ion from the lead. You're going to see that the silver goes to 2 times 10 to the minus 4. Okay, and the question is, that's because that's my silver ion concentration initially, and 2x. And then at equilibrium, some of it's going to go into solution, minus y plus y plus y. Why is that? That's because that's the chemical that is going to dissolve. And I put y in here just because that's a second variable. So this is what I have right here. And what you can do is you can say that because the equilibrium constant for silver is so much smaller than the equilibrium constant for lead that the 2x value right here is negligible. Okay, that is the amount that is dissolved from the silver is going to be small compared to the amount that is produced from the iodide. So when we solve this math right here, you're going to get this constant, this mathematical expression, and then you can solve for the x value here, and then you can plug it into this math equilibrium, and you can get an iodide concentration. Double check your work. Take 4.25 times 4.256 times 10 to the minus 13, multiply that by 2 times 10 to the minus 4, and see whether or not you're going to get this value that is equal to 4.26 times 10 to the minus 13. Okay, that's basically just setting up the mass action expression. Once you get this, then you can solve for the second equilibrium. And why can we do this separately? Because you can treat this as a separate problem, because look at the difference in the equilibrium constant. Okay, then we can put in the second expression here, and then if you go through the math, I won't go through that because we don't have enough time. I want to move on to KF. Then you can solve for the y value here, and if you solve for the y value here, what you would get is the concentration that comes from the lead. So these are the concentration that you need, because look at the question. If sodium iodide will is added, will silver iodide or lead iodide precipitate first? Look at the smaller value. The smaller value is 4.256 times 10 to the minus 13 versus 1.88 times 10 to the minus 3. The smaller number means that it's going to be the least amount that you would need to get a precipitate. That means that the silver iodide, and it makes sense just because of that KSP value right here, is going to precipitate out first, and then the lead iodide will precipitate out second. So take a look at this. Again, it's a lot of math. Try and make sense. But I'm giving you examples here that are a little bit more difficult. That way you can see how the math is done, and hopefully you know how to approach this. But I really wanted to get to this part right here. This is the last part of equilibrium. And the reason why this is important is because your evaluative report and probably experiment number 5 deals with complex formation, KF. And you've already seen KF in terms of iron thiocyanate. You guys got an equilibrium constant for that particular reaction. You establish a KF value for that. That was experiment number 2. Okay, so what you will find is that unlike solubility, KF values are very large, very large. You're going to see equilibrium constant in the order of 100, 1,000, 10 to the minus 8, 10 to the minus, not 10 to the minus 8, 10 to the positive 8, 10 to the positive 30, 10 to the positive 90. It goes practically to products. Okay, so let's take a look at this. This is silver chloride, and you know the silver chloride precipitates out in solution, which means that it doesn't form, doesn't dissolve that very readily, but the formation is going to be very large. But if we take silver chloride and we add ammonia, and you guys did this in experiment number 3, okay? If you add ammonia, you actually did this experiment as well in chemistry 152. Look at, I believe, experiment number 2 or 3 in chemistry 152. If you take silver chloride and you add ammonia to it, what happens is that the silver chloride dissolves. And the reason why it dissolves is because the formation of silver diamine silver has a stronger equilibrium than silver chloride. And that's the chemistry that you see right here. What happens is that the silver will react with ammonia and give you this particular chemical. And so your net reaction is this right here. Silver chloride plus ammonia goes to silver diamine. Ammonia is called amine now, okay? In chemistry, it's not called ammonia. Diamine silver plus chloride. And if you take a look at that right there, it basically causes the silver to dissolve in solution. And that's what you see in this picture right here. Let me clear this for you. Here we have silver chloride. And what happens is that we add ammonia to this, NH3, probably add ammonia via ammonium hydroxide. Ammonium hydroxide will break down to water plus NH3. Okay, so we put that and look what happens. That precipitate is gone, it's dissolved. Why? Because we don't have silver chloride anymore. We have diamine silver. Diamine silver, that's this compound right here. So we basically reduce the solubility of silver chloride by occupying silver in a secondary reaction. So that's basically it. And this chemical right here, this reaction right here has a Kf, an equilibrium constant, Kf. So in terms of this particular case, we take a look at this reaction. It's products over and the net ionic equation that. So that's what we are paying attention to. The product is diamine silver over silver times ammonia squared. And look at that equilibrium constant, 1.7 times 10 to the positive 7. Okay, so it's a very, very large number. And when you solve these types of problems, you can assume that practically all the chemicals goes into the product based on the limiting reagent. And you guys did that in experiment number 2. So the reason why I want to show you this table is because this chemical right here is the chemical that you guys are going to be working with in your evaluative report. You guys are going to be synthesizing not so much a cobalt salt, but the nickel salt, NiEN3, where En stands for ethylene diamine. You guys will learn more about ethylene diamine in the future. So I don't think I have nickel in here, but we do have cobalt. And it's going to be very similar because cobalt and nickel are practically next to each other. Let me see, here it is. Okay, this is the chemical you want. It's going to be the nickel, En3, 2 plus, and look at that equilibrium constant. It's 2.1 times 10 to the positive 18. As soon as you put a little bit of ethylene diamine into nickel ions, precipitate happens. Why? Look at the equilibrium constant. 2.1 times 10 to the positive 18. If you had cobalt, it's even more spontaneous. You even get more chemical going to products. Okay, look at that equilibrium constant, 4.9 times 10 to the positive 48. In fact, if you just peruse these values, you can see that they go up as high as 48. There's 30 right here. There's, let's see. Yeah, 48 seems to be like the highest value. And you get small numbers as small as, no, this one's 42. Well, you can see that they readily go to products, okay? The smallest number is probably 5 times 10 to the 5th, but still a large number. In other words, you put these chemicals into solution, you get the formation of these products right here. So let's take a look at this problem. You've got zinc, tetraamine zinc compound. It has an equilibrium constant of 2.8 times 10 to the 9th. A solution is made by 1.1 times 10 to the minus 3 zinc nitrate. The nitrate's going to be a spectator. It's just a zinc. And and you know that nitrate salts are soluble. So you put 1.1 times 10 minus 3 molar zinc nitrate, you're going to get 1.1 times 10 to the minus 3 zinc ions. Why? Because nitrate salts are soluble. And you've got 0.150 molar ammonia. After the solution reaches equilibrium, what is the zinc equilibrium concentration? It's not going to be zero. It's not going to be zero, but it'll be very, very small. So this is the reaction we have. This is the ice table that we generate. Let me go back. Okay, we know that this is the concentration of the zinc. How do we get that? That's from that right there. This is the concentration of the ammonia. How do we get that? We got that right there. And then we get zero products. You always start your reaction, if it's beginning, zero products, unless you have a common ion, in which case you need to put the common ion in the initial line. This is not a common ion. Okay, so we get zero. Then we look at the chemistry. And the chemistry tells you that this right here is very, very large, which means it goes practically to products based on the limiting reagent though. You guys know this from experiment number 2. We made the iron concentration in test tube 5 so much bigger compared to the thiocyanide that the amount of products that we got in test tube 5 was based on the limiting chemical thiocyanide. And we said that that's the amount of products we produce. Well, very similar to this example right here. We know that the smaller amount is 1.1 times 10 minus 3. So that's going to be your limiting because it's a 1-to-4 ratio. Okay, so we're going to say minus x, and then instead of minus 4x here, because remember reactants are minus, they're going to get depleted, we just put 1.1 times 10 to the minus 3. Why don't we put 4 times 1.1 times 10 to the minus 3? Remember, the zinc total is 1.1 times 10 minus 3, so you can't make it 4 times bigger because there's no way to create matter. You're using up that limiting reagent. That's why you don't put minus 4 times 1.1 times 10 to the minus 3. You just put minus 1.1 times 10 minus 3 because that's all the zinc that you have. Okay? And then the amount of zinc amine that you form is also 1.1 times 10 minus 3 because remember, your product is based on your limiting reagent. We did that in experiment number 2. Now we have this as our equilibrium line. 1.1 times 10 to the minus 3 minus x, 0.15 minus 1.1 times 10 to the minus 3, and we have 1.1 times 10 to the minus 3 as our zinc nitrate. What we can do now is stick these, because these are the chemicals at equilibrium, put that in the mass action expression, okay, and then solve the math. So what we have in the very top is zinc, tetramine zinc, at the bottom is zinc and ammonia to the 4th. So what we have is, what we did is, I'm going to make this value say x, because that value, I could make it y, for example. That value is our answer. After the solution reaches equilibrium, what is the concentration of the zinc that remains? That answers that question. How much of it is at equilibrium? So what I have here is, this is my products here. This is 0.150 minus 1.1 times 10 to the minus 3. That's that quantity right there. And notice I put it to the 4th. And this quantity right here, I can just name that y. Okay, I can just name that y. It's generally 1.1 times 10 to the minus 3 minus x. How much of that is removed? And it's not zero. It's not zero. In order for this mass action expression to be obeyed. So we have this math problem right here. And when we solve for this quantity, we get this quantity as 7.99 times 10 to the minus 10. And that's your answer. That's the amount of zinc at equilibrium based on the values that we have. It's basically just the math right here. So let me clear this out real quick so that I can show this again. This right here is the mass action expression. This is Kf, and this is this expression right here, zinc NH3 4 over that concentration over zinc plus 2 times NH3 to the fourth. That's equal to this value right there. We know what this is. We know what this is. We're solving for that. And when we solve for that, we get this value, because that's what the question is asking. What concentration of zinc remains? That's the concentration at equilibrium. The concentration of zinc that remains is 7.99 times 10 to the minus 10. Very, very small, but not zero. And if you take these numbers, 7.99 times 10 to the minus 10, plug it in here, 0.1489, and raise that to the fourth power, and 1.1 times 10 to the minus 3, and you solve that, you should get very close to 2.8 times 10 to the ninth. Okay, so in these types of equilibrium problem, you got to have a different mindset, because the reaction practically goes to product, and the question is, what are your concentrations at equilibrium? So if it practically goes to product, that means that your product is going to be, that concentration is based on your limiting reagent. How much, which chemical gets used up first. And that'll be the concentration of your product. All you've got to do now is figure out, okay, the chemical that's a limiting reagent, yeah, that's going to dictate how much product I have, but it's not going to go to zero, because if this was zero right here, that term becomes undefined, okay? That term becomes undefined and you can't solve that math. But it's very, very small. And that's what we have right here, okay? Yeah, these types of problems are a little bit more complicated from what we have. It's because the math is much more complicated, but it's just the math. I'll give you this last example right here. We have silver iodide and silver dicyanosilver. So we have these two reactions. We've got silver plus cyanide, and this is a single displacement reaction. And the single displacement is that the cyanide substitute for the iodide, and you get dicyanosilver plus iodide. And the question is, what is the K equilibrium for this reaction? That's what the question is. So I give you, in this particular problem, you're going to be able to find, oops, don't know. You're going to be given the KF value for, or the KSP value for silver iodide. Why is that a KSP? Because it's a chemical that is dissolving. And you're also going to be given the, oops, what's that happening? Sorry about that. Okay. You're also going to be given a KF. Why is it called a KF? Because you're forming a complex ion. Remember, when something's dissolved, it's a KSP. When something forms, it's a KF. So you're given these two equilibrium values, and the question is, what is that? And the way you solve this problem is, go back to our first lecture on equilibrium, where we dealt with equilibrium constant. When we dealt with equilibrium constant, I see I'm running over, and this is the last topic that I'm going to be talking about. You saw that you can take equilibrium's expression or constant, and you can multiply by a quantity to get the new equilibrium constant based on the math that you do to that reaction. Well, take a look at this right here. Okay, I'm gonna delete this. Clear. If you take these two reactions and you add them up, the silver will cancel, and what you get here is AgI plus 2Cn goes to AgCN minus plus iodide minus. Isn't these two reactions added equal to the net reaction here? Well, when you add two reactions, what do you do to the equilibrium constant? You just, to the equilibrium constant? Well, basically, it's like taking this and multiplying by that, or adding them together. And if you add two reaction, you take the equilibrium constant and you multiply them by each other. So the new equilibrium constant, this one that we're figuring out, is nothing more than KSB times KF. And that would be your equilibrium. Why? Because to get that net equation, you're simply adding the two. And so that's what you see right here. Okay, that's what you see right here. You're just multiplying them out, and then that's the equilibrium constant that's found from that. Don't make something new. Just figure out what is given and rearrange the equations so that you can get the right equation that is what the question is asking for.